Hello, 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 and welcome back, Algebra 2. Today we're going to continue our discussion on asymptotes and holes. Additionally, we're going to introduce graphing rational functions today because it starts to wrap everything up really nicely. Piece all of the information we've learned so far in a nice, beautiful way. Also, great visual representation, and it's something you're going to need to know if you're moving on to higher math courses. So buckle up, let's get on to it. This is the first part of the lesson, and I'll address the second part at the very end. Yeah, hello, it's me. I'm so glad you're here, and welcome back. Let's get this show on the road, shall we? Let's go. Let's go. Let's go. Let's go. Oh man. Okay. Public service announcement. Really, 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 really important, you guys. First of all, congratulations for making it to the last week of school. You did it! Oh my gosh. Okay, so big deal. Since this is the very last week of school, deadlines are changing. I have hard deadlines for school, for grades. You have hard deadlines in order for me to meet my deadlines, okay? So, normally, I let y'all turn stuff in on Sundays, 9 p.m. This is changing. This is your announcement right now. Every assignment that I post this week, which is today's lessons, and also there's one more day of lessons, so you have 2 days of lessons, will be due by Friday, June 5th at noon. No ifs, ands, or buts. So everything I post, anything that is due, including the homework, including any videos I have you watch, including anything at all, okay? Every single thing is due by Friday, not Sunday, Friday, June 5th, 2020 at noon. Okay? This is because I have hard deadlines that I have to meet. I cannot have them. I know I cannot meet them if 185 of y'all are coming in with your work super late on Friday, okay? So, no exceptions. If you turn something in late on Friday, it's going to get a 0. Okay? Anything afternoon, I'm not even adding in. I'm just going to give it a 0. I don't even care if you did it. You have to get absolutely every single thing done this week by noon. PSA, you have ed puzzles this week, okay? Like 2 of them today. So make sure you do not wait until the last minute to do those because they're worth a lot of points. Okay? No exceptions on this. Every assignment is due by Friday, June 5th, 2020 at noon. Okay? Please do not miss this piece of information. It's very, 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 very important. I'm very happy that it's the end of the year. I know you guys are tuckered out. Hang in there. Shoot, 12:01. Get crazy. Pop open a Dr. Pepper. You know, maybe you call up your friend. You're like, woohoo, summer started. Ooh, ooh. Yeah, maybe you cannonball into a pool. I don't know your life, but you do you, boo. You do whatever you want, but you just got to get your stuff in by noon on Friday, June 5th. Okie dokie? Cool. Okay. So before I just dive right in, I just want to recap. Last time we were here, we were talking about holes and asymptotes. Specific to rational functions. So we talked about 2 different things last week. We talked about if a graph or a function is continuous, which means your graph and function continues forever and ever and ever. Forever, forever, ever, forever, ever. Your graph is continuous, okay? And we said that when a graph is continuous, its domain goes from negative infinity to positive infinity. Or it has a domain, of all real numbers, okay? All real numbers. All real numbers can also be rewritten like this. Now, don't judge me because I'm using a mouse on a pad, not a cool paper thing. So all real numbers takes on this symbol. It's like a bold-faced R. All real numbers. Let me see if I can make that better. It's like 2, that wasn't very good. looks like this. Boom, boom, R. Yeah, you get the idea. All real numbers. That just means the domain is negative infinity to positive infinity. It's the same thing. Mathematicians use this notation all the time. And so when your graph continues forever and ever, you never have to pick up your pencil. Your graph is continuous, and so is your function. But there's another time, there's another option as well. You could have a graph or function that is discontinuous, aka meaning you have to pick up your pencil, your writing utensil, to continue drawing that graph. Okay, and when we're talking about things that are discontinuous, we have a couple options. Okay, so there are two types of discontinuities, the plural of discontinuous, two types of discontinuities. Okay, there is a removable discontinuity, meaning that we can remove something from the function. We can move it, we take something away. And there's non-removable discontinuities. I can't get rid of this at all. So a removable discontinuity is a hole, okay? A removable discontinuity is a hole. That's something I want you to know. So that might mean your graph looks something like this. Oof. Right, here's a line with a hole. That's a really bad hole, but you get it. And if a removable discontinuity is a hole, then removable discontinuities are holes, and this happens when I'm canceling out factors from the numerator and the denominator. Something, when they're factored, cancels out, which means I end up with a hole. Is it coming back to you? It should. If not, write it down, okay? So if a removable discontinuity is a hole, then a non-removable discontinuity is an asymptote, okay? And it's actually a specific asymptote. It's a vertical asymptote. I should write VA. And VA stands for vertical asymptote. Now, this happens when your denominator is equal to 0, which we know we can never have our denominators equal to 0. That's undefined, okay? So if your denominator is equal to 0 and it doesn't cancel out with any factors from the top, you have a vertical asymptote. And that's kind of where we left off last week. So, do you guys remember when I used to wear this shirt? You guys loved it so much. It was my holy shift. Look at the asymptote on that mother function shirt. And I'm really sad because I don't get to wear it this time around. While we're learning about that is a rational function right there. That function on my shirt is f of x is equal to x over x minus 1. I have it on right now. You can't even tell, but I'm going to have it on this whole week while we're talking about asymptotes, okay? So, holy shift, look at the asymptote on that mother function. You guys will talk about shifts later, but I want to talk about the asymptote. Wow, okay. I'm just going to erase that there. The asymptote on the mother function, on our parent function, if you will. So, asymptotes happen when our denominator, x minus 1, is equal to 0. So let's look at my shirt, okay? Because I would be wearing this and we would be talking about this if we were still in my classroom. So if I set my denominator equal to 0 to find out where my asymptote is, I would solve x minus 1 equals 0. I would add 1 to both sides. I end up with x equals 1. That's where my vertical asymptote is, okay? My vertical asymptote is that x is equal to 1. And if you look at this shirt, here is my x-axis and my y-axis. This is 0. This over here is positive 1. And check it out. Right here where this dashed line is, if I'm looking at the scale on my shirt, this is 1, 2, 3, 4. That is exactly where my vertical asymptote is. It is at x equals 1, which is amazing. It's awesome sauce. So if we were in my classroom, I would still be wearing this shirt. Think about the asymptote on my mother function. How do I find that? When my denominator is equal 0. Got to figure out where that is so I can put in a vertical asymptote. Also notice things don't cancel here. So if it did, I would have a hole. If I had x minus 1 on the top, I would have a hole, but I don't. I have an asymptote. Sick! Okay, so notice I have my little icon up here. I want you to take notes on this. Asymptotes. We've talked about it before, but we're going to talk about it again because they keep popping up all over the place. So an asymptote is a line that your graph approaches as x or y increases. Doesn't matter which direction it's going in, if it's horizontally or vertically. But the most important part about this is an asymptote is a line that the graph approaches but never touches. So because I'm cheesy, I like to introduce asymptotes as MC Hammer. Do that every time. MC Hammer. Dun-na-na-na, dun-na, dun-na. Can't touch this. Ba-na-na, ba-na, ba-na. Can't touch this. Oh, 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 oh. Can't touch this, right? Okay, so your asymptotes, your graph is getting really, really close, but never touches. Okay, if you think back to our prior knowledge, exponential growth and decay had asymptotes. So we're going to kind of expand on that. So we have two different types of asymptotes. We have vertical asymptotes, which I graphed in red for this portion. So vertical asymptotes, and here are some characteristics about vertical asymptotes that I want you to take down as like little bullet notes. Okay. You can have more than one vertical asymptote, okay? And I'm even going to write next to this VA. This is how I denote vertical asymptote and many other math teachers, mathematicians, people in math in general. You can have more than one, all right? Which is kind of weird, but trust the process, okay? You can have more than one spot where you potentially could be dividing by 0. That's all that means, okay? Now, your vertical asymptote is going to happen at x equals a if you have a non-removable discontinuity. Again, remember, non-removable just means that it doesn't cancel with the numerator, with the factor in the numerator and the denominator. So this is going to occur wherever denominators are equal to 0 that do not cancel out. Okay, so to be very specific, in this example, x over x plus 5, right? Nothing cancels. I don't have the same factors on the top and the bottom. X equals -5 is where my vertical asymptote is. That's what I mean by like x equals a. It's this part is where your denominator is equal to 0. So here's what a graph would look like with my vertical asymptote at -5. Notice my vertical asymptote has a red dashed line. There's -5. That's exactly where it is. Voila. Okay. Now, horizontal asymptotes, or I'm going to call them HA for short, not ha ha ha, horizontal asymptotes, have a couple of characteristics as well. Okay, so you can only have at most one horizontal asymptote. You can have 0 horizontal asymptotes, but you can't have more than one. It's not like vertical asymptotes. You can only have one horizontal asymptote. And you're going to have to compare the degrees of the numerator and denominator in order to figure out where your horizontal asymptotes are. Okay, so this is where you're going to have to compare some things. If the degree of your numerator is m and the degree of your denominator is n, then we're going to use these following rules. Okay? If your numerator is less than the denominator, you have a horizontal asymptote at y equals 0. If your numerator is larger than the denominator, the degree of the numerator, then you don't have a horizontal asymptote. And if your numerator degree is equal to the denominator's degree, then the horizontal asymptote is at the ratio of the coefficients. Now, I know that's a lot. You really need to get down these notes. And with practice, which we're going to do some practice today and even later, hopefully it will become a little bit more clear. But these are the criterion for determining horizontal asymptotes. Okay? And I guess I should mention that your in order to do this, in order to compare the degrees, you're going to need to be in standard form, not factored form. So, for example, this is a graph where we have a horizontal asymptote here moving around. This happens to be at 2, 4, 6, 8, 10, at y equals 2, because it's at the y-axis at 2. That's where my horizontal asymptote is in this picture. So we're going to get some practice with identifying where vertical and horizontal asymptotes are, and then even more when we actually get to the intro to graphing. Okay? So we're going to do 3 examples to get down horizontal asymptotes. But only after we have a meme break, okay? So here is a very popular meme of Gandalf saying, "You shall not pass," as a vertical asymptote, right? He's got his thingy-majig, whatever this is called, I don't even know, don't ask me. And it's, producing light up and down, and he says, "You cannot pass this point," right? That is representing our vertical asymptote right here. This part, our graph is going to get really, really close to, right? Look, here's part of our rational graph. It's going to get really, really close to, but never touch. You shall never pass a vertical asymptote. I just thought that was kind of funny. Horizontal asymptotes, okay? 3 examples, like I said. 3 examples of identifying our horizontal asymptotes. And I kept my my notes right here to the right so we can see them, our comparison about comparing our degrees. Note, you have to be in standard form. So I'm going to write that down. Standard form. Okay, so notice this is not in factored form. I couldn't factor the denominator if I wanted to. So for this example, again, write this down. X plus 7 over x squared plus 3. I need to figure out where my horizontal asymptotes are, okay? So I notice that the numerator is less than the denominator, right? This is x to the first over x squared. If I zoom in on that, x over x squared, that tells me that my numerator is less than my denominator, which means I am here. M is less than n, so the horizontal asymptote is at y equals 0. Okay, so we literally have to just compare numerators and denominators. So it's also going to have 2 vertical asymptotes because I can factor the denominator. So I take back my statement. Well, it's interesting. You'll see. So it's going to have 2 vertical asymptotes. So you set your denominator equal to 0. Right? My denominator is going to tell me where my vertical asymptotes are when I set them equal to 0. So let me do it. X squared minus 3 equal to 0, right? Add 3 on both sides, you get x squared equals 3. And if I take the square root of both sides, I get x equals plus or minus radical 3. So, I guess I could factor this into x plus rad 3 times x minus rad 3, but that's a little crazy. But I do have 2 vertical asymptotes at radical 3 and negative radical 3. And my graph would look like the following. Okay, let me get rid of my green stuff over here. So look, I have my horizontal asymptote at y equals 0. This is something we said, y equals 0. Here's y axis. Here's my horizontal asymptote. It's kind of hard to see, but it is right along there. And then these 2 vertical asymptotes are happening at, this is negative radical 3 on the left, and this is positive radical 3 on the right. Okay, so I just compared my numerator and my denominator. This degree was less than this one, so I followed my rules, and that said y would have to equal 0. Here's another example. Notice now my example's in standard form, not factored form. So if I had x squared plus 2x plus 1 divided by x minus 1, and I want to know where my horizontal asymptotes are, here's my rules again. I have to compare the degree of the numerator to the denominator. So looking at our numerator to the denominator, what do you notice? Okay, we notice that the numerator degree is bigger. X to the power of 2 is bigger than x to the power of 1, right? So if my numerator is larger than my denominator, that means I'm actually working with this. M is greater than n, which means yes, I'm zooming right into x squared and x to the first. That means there is no horizontal asymptote. I don't have one. And that's okay, right? I could have at most one, and this one I just don't have one. This one actually goes into oblique asymptotes, which we're not going to talk about at all. It just means the asymptotes aren't exactly horizontal, they're at a slant. But this graph does have one vertical asymptote. Remember, vertical asymptotes happen when our denominators are equal to 0. So I would say x minus 1 is equal to 0 to find that. Add 1 to both sides, I just get x equals 1. And if I graphed it, I would have no horizontal asymptote, but a vertical asymptote at x equals 1. So this is what this graph looks like. Notice that I have my vertical asymptote at x equals 1. So this is the point 1, x equals 1. And I don't have any horizontal asymptotes, but you'll notice my graph kind of looks a little weird. That's because it has a oblique asymptote that I'm not going to get into, but basically the asymptote runs kind of like at a diagonal, runs at a slant. Again, not going to get into that. That's kind of a very complex idea and has a lot of rules, but we're just going to talk about the basic horizontal asymptote. So nothing running horizontally, no, though. And lastly, again, this is in standard form. If I have negative 3x plus 5 divided by x minus 4, where's my horizontal asymptotes? So I want to again compare my numerator to the denominator. Notice that the degree of the numerator, I have negative 3x to the first plus 5 over x to the first minus 4. That's that invisible 1. So comparing these denominators, I notice that they're equal, right? The numerator degree, the first degree polynomial, is the same as the first degree polynomial on the bottom, which means that the horizontal asymptote is going to be the ratio of the coefficients. So zoom in on this little box here. That ratio is negative 3 over 1. Okay, so my ratio is negative 3 over 1. So my horizontal asymptote is going to be at negative 3, right? I got negative 3 from the numerator, negative 3, 1 from the denominator because there's a hidden 1 being multiplied by this x. Negative 3 divided by 1 means negative 3. So that's where my horizontal asymptote is going to be located. It also has a vertical asymptote because I can potentially divide by 0. So if I set my denominator equal to 0, I will find exactly where that happens. X minus 4 is equal to 0 when x equals 4 by adding 4 to both sides. So I have a vertical asymptote at x equals 4 and a horizontal asymptote at y equals 3. Now, this is what that graph looks like. Okay, notice that we have our horizontal asymptote at negative 3. Here's negative 1, negative 2. This is negative 3. and that's exactly where we have our horizontal asymptote, and then our vertical asymptote occurs at x equals +4. Okay, so how do asymptotes laugh? Va, ha ha, ha ha. I thought that was kind of funny. To get it, vertical asymptote, horizontal asymptote. Okay. So I thought that was kind of funny. And then I saw this on the internet and I was a little bit perplexed and I was like, what? But I guess someone made up a like a cartoon about denominator dog, which looks for holes in asymptotes. So he's digging holes and sniffing asymptotes, looking at your denominator of all your rational functions. Okay, holes again are if they cancel, that's a removable discontinuity. Asymptotes are if they don't cancel, when your denominator could equal 0. So what's next for you guys? You guys are going to watch 2 Edpuzzle videos that's going to recap a lot of this and start piecing together what rational functions look like and how we would start to make connections about the graph. So I've shown you pictures of the graph that match what we've talked about, but you haven't actually done anything with the graph yet. So that's what this is going to dive deeper into. And these are courtesy of Miss Perez. I did not make these videos, but I love them. I watched them, and they're fabulous. You guys are going to really like them. They're very clear. They are not long at all. I think the longest one is 15 minutes, so they're super short, way shorter than my videos. But you're going to watch 2 Edpuzzle videos. That's your homework, okay? But I want you guys to make sure you're taking notes with these, because some of the outcomes that happen are a little bit surprising. Also, I additionally want you guys to take notes, and also take your time, because these are worth a lot of points. In Google Classroom, the Edpuzzles are worth like 100 points each, okay? So I want you to take your time on these and pay close attention. Remember, you have until Friday at noon to do these. So they're worth a lot of points. Take your time. You do not get to redo Edpuzzles. So just beware of that, okay? Take notes, follow along, and try your best. I think you're really going to like them. And then next time when we meet, we're going to be continuing wrapping everything up together, and I'll be giving you guys a extra credit opportunity as well. So that is all I have for you right now. Thanks so much for joining, and I will see y'all soon. Bye.